Okay. You know what? I bet that's exactly what happened. And I definitely need to, it's telling me I need to turn this down. All right. Let's see. Does it like that setting better? Nope. I wondered why in the past it would black out some. And I think, hey, Caleb, I think that is why. I think it's because it was running out of storage space on the internal memory. And I needed to switch it over to the SD card. Okay, good. I learned something. I was ready to pick up where we left off before Caleb so rudely interrupted me last time just because it was the class was over. Seriously, everybody listen. If I get going and I lose track of time, somebody let me know when it's the 5 minutes after, or 5 minute, the 25-minute mark, so I can let y'all out of here, because I don't want to keep y'all later than the class time, because other professors and instructors have classes and y'all have other things y'all have to get to. So thank you for that. Seriously, I really do appreciate it. Now I'm still going to give you grief about it, but RJ Vilkeman. I don't know. I told everybody else that I graded your bonus exams. I sent out the scores to you in emails. Overall, it was much, much improved. So it should definitely help everybody's grade. It was successful enough that I've decided to do it to my other 2 regular classes as well. So they don't know it, but they all owe you a debt of thanks. All right. Snell's law and the index of refraction. We've got a ray of light passing through some medium with index of refraction n sub 1. What is n sub 1? What is the index of refraction? The speed of light in a vacuum divided by the speed of light in that medium. That is the definition of the index of refraction. And if you ever get to a class where you study light and how it propagates as a wave, you will actually analyze how slowing it down causes it to change direction. Okay. And that's what causes light refraction. Here we're just going to use it as a definition and look at how it behaves, how it causes light to behave. In medium N1, the light ray comes in and strikes the interface between the 2 media. Little language for y'all here. Medium does not mean between small and large. It actually does mean between, but it is the singular form of media, the plural. So when you hear me talk about the medium and the media and the interface between them, that's what I'm talking about. You're going from the index of refraction of N1 to something with an index of refraction N2. Now, looking at this picture, what can you tell me about the N1 and N2 relative between them? No. Well, and maybe it's not exaggerated enough here. theta 1 is greater than theta 2, but if that means that, well, sine of theta 1 is greater than sine of theta 2. So what does that mean about N1 and N2? N2 has to be greater than N1. So when a ray of light transitions from a medium with a lower index of refraction into a medium with a higher index of refraction, it will bend towards the normal, towards the perpendicular between them. Higher index of refraction pushes the ray closer to the perpendicular. Or, going the other way, this incident ray, because it's going into a medium of lower index of refraction, bends away from the normal. Now, that's the phenomena that we want to look at right now. What happens? I make theta 2 a little bit bigger. Theta 1 gets a little bit bigger. Make theta 2 even a little bit bigger than that. Theta 1 gets even a little bit bigger than that. And at some point, this theta is going to be so great that this one gets all the way to 90 degrees, parallel to the surface, to the interface between them. What does that mean about Snell's law? When theta becomes 90 degrees. N1 becomes unity. Or sine theta 1, what's the sine of 90 degrees? 1. At that point, N1 has to equal N2 sine theta 2. Or N1 divided by N2 equals sine theta 2, or the inverse sine of N1 over N2 equals theta 2. That is a special condition where it's called the critical angle, or the angle of total internal reflection. Okay? If you get any further than that theta sub c, that critical angle theta, then this refracted light would have to bend more than 90 degrees. Well, what would be the sign of more than 90 degrees? One of two things would have to happen. Either the light would have to start refracting less, which it can't do because physics, you know. Or the sine of theta would have to become greater than 1, which can't happen because mathematics, which describes somebody? Nope. Physics, thank you. Sans sneeze. Yes. What happens at this special angle is called total internal reflection. Think about laying on the bottom of a swimming pool and looking up. You look straight up and you can see the sky above, people overhead, flying, birds flying through the air, but only so far, and then you just get to where all you can see is the inside, the bottom surface of the water with everything reflecting back. And you can't see anything through anymore. We didn't get to it last time. I brought this prism I have from a very expensive piece of optics. And I'm going to pass it around and y'all can look at it. But I also want you to look at something else. If you put your finger, if you're holding this looking through the clear side, if you hold it looking straight ahead, straight into it at the 45-degree angle and put your finger behind it, you cannot see your finger. All you can see is whatever's reflecting up through here. But if you start bending it this way, so you're now no longer looking at 45, but something more, at a greater angle, you can see that line of total internal reflection pass right over until you can see right through and see your finger. Okay, so hold it, this black piece up here, put your finger through and do that. That's a good example of total internal reflection. No. Here. Hold it that way. Put your finger behind it now. You see it happening? All right. What's the first technology, modern technology you can think of that depends wholly on this phenomenon? Nope. Nope. Actually, binoculars and telescopes that use this kind of optics where they, the light gets transmitted through these mirrors and, it becomes very critical for those. But there's another one, more common, that relies totally, completely on this phenomenon. That without it, the technology simply wouldn't exist. We'd have binoculars, we'd have telescopes, even if we didn't have total internal reflection. But there's one thing we wouldn't have. I know one of you knows it. No? Got a guess? Say again? You were about to guess something. What was it? No, say. Periscopes? Yeah. No, not periscopes. In fact, mirrors are never totally 100% reflective. With a mirror, there's always going to be some light transmits through to the other side. Not necessarily any that you could observe or detect, but some will pass through. The best mirrors, the most expensive mirrors, are only like 99% reflective. Say again? No? Fiber optics. Yep. We could not have fiber optics if it wasn't for this in total internal reflection. That's how fiber optics work. That's why you shine light in the end of it. You don't see light leaking out the sides of that fiber optic cable. Yeah, okay. No harm, no foul. You don't see light leaking out the side of that fiber optic cable. All the light you put into one end comes out the other end. And that happens because of total internal reflection. If you had a mirrored optical cable, optical fiber that you relied on to get that light all the way to the other side, you would lose that light. It would be a very lossy transmission system. With total internal reflection, you don't get any losses. That light, whatever light you pipe into one end of it, comes out the other. Now, that's assuming all of your interfaces and connections are totally, perfectly lossless, which is not going to happen. I think you're You were the one saying you've run fiber optic cables. Yeah. Do you ever actually get total lossless connections? No. But this is what makes fiber optics work. Because even if you took a glass rod, a long glass rod as long as a fiber optic cable, and you mirrored the outside surface, you're still losing a little bit. You're losing like 1% of the light every time it hits that mirror and comes out, and so, for every 100 reflections, you're going to basically lose your light. Now, this is also why, if you've ever been bow fishing, have any of you ever gone bow fishing? No? Okay. Yeah, you have to aim below the fish because the fish looks like he's over there, but he's actually right here. That's why swimming pools and lakes always look to be shallower than they really are. Say again? Yeah, well, I wouldn't go that far, but yeah. You're always going to have a little more depth to work with than you can see. Have any of you started the homework for this chapter yet? Okay. Has everyone turned in the last week's homework assignment? No? There's a whole slew of zeros that are going to pop into your grade that all the bonus exams aren't going to help. Okay. I want to work through one of these examples with you anyway. Before we go on, because I want you to see I want you to actually go through the mechanics of working the problem. So get out your calculators to help me with the arithmetic. Let's start with this first example they do. Example 23.8. Refraction through a pane of flat glass. Light traveling in air strikes a flat piece of uniformly thick glass at an incident angle of 60 degrees, as shown in figure 23.24. If the index of refraction of the glass is 1.5, what is the angle of refraction theta sub A in the glass? And what is the angle theta sub B which the ray emerges from the glass? So let's draw our picture. Here is our flat piece of glass. Here is our normal to the glass. This ray comes in at 60 degrees. N equals 1, N equals 1.5, N equals 1 again. So since 1.5 is greater than 1, what do we know about the light coming through? That theta is going to be less. If N is greater, theta sub, what is this one, A, is going to be less than the 60 degrees because N sub inside is greater than N outside. If the index goes up, the angle has to go down because they have the N times the angle has to be the same on both sides. So, what is theta sub A? That's the first thing we're going to solve for. And Evan, tell me what to write. Huh? No, we're going to start with Snell's law. Okay, yeah. So in this case, what is N1? 1 times sine of 60 degrees is equal to theta sub A. All right. So we can say sine of 60 degrees divided by 1.5 is equal to the sine of theta sub A, or theta sub A is equal to the inverse sine of sine 60 divided by 1.5, which is, somebody with a calculator?
35.26.
35.26 degrees. All right. Now we're coming out the other side of this glass. Now, since these are parallel lines, we know that this theta is equal to that theta. So that's 35.26, which gives us this theta. What do I write down? RJ. Oh, no, go ahead. Got a volunteer. Bingo. Exactly. So, well, there's not really a whole lot of algebra to do. These are all known numbers, so what's 1.5 times sine 35.26? So all of that is equal to sine theta sub b, and therefore sine theta sub b is equal to the inverse sine of 1.5 sine 35.26. Which equals if you don't round off in the middle, then it'll come back to a perfect 60, or it should. That's why it's generally a good idea when you can do everything in one calculation without rounding off interim answers, you'll get a more accurate result. You still need to be conscious of significant digits in your final result, but you don't need to add more error by doing, every time you round off in the interim, you're adding a little bit more error. So, the light coming out the other side is exactly equal to the light that came in. It's just offset by some amount. Do they ever have us analyze how much that offset is?
What did you say it was going to?
Glass. No, and if you want it to match what they say in the book, this is where they put the dotted line showing that the two rays are parallel. It's going through glass with an index of refraction of 1.5. So, everybody keep your calculators out. We're going to do another one. This time we're going to look at the apparent depth of a pool of water. Here's the bottom. Okay? And here's the top. Now, if someone wants to know how far down this is, or how far down it looks, you come over some distance here, and you look in, some angle theta, where in here is air, so it's equal to 1. In here, this is water, so N is equal to what, 1.33? Looking at 23.9. Yeah, 1.33. Which means theta 2. To come down here to the bottom. Forgive me for messing up the line, but if you follow the line that you were actually looking at, it looks like the bottom of the pool is up here, when in fact it's down here. And that's more exaggerated than the one in the book, but I don't have calibrated eyeballs or fingers, so I'll just try to make it big enough that you can tell what I'm drawing. Okay, they're saying we're going to calculate the apparent depth given a real depth of 1 meter. All right, well, let's see how we can do that. This is the apparent depth. This is actually 1 meter. Okay? What angles do they give us? Ah, they don't. Well, what can we say? We can say that 1.1 times theta 1, or sine theta 1, is equal to 1.33 sine theta 2. And that's the starting point. Yeah, I've put the angles backwards. No, see, no. I'm pulling the plug on this right now because they're talking about small angle approximations, and I don't want to go into all of why that's true. I know you probably know that for a very small angles, sine of theta is approximately equal to theta, and tangent of theta is approximately equal to theta. But that's let's forego that. What can we know about this? Let's pick numbers for theta. Say theta 1 is, let's say it's a small angle, 10 degrees. Then what's the sine of 10 degrees? Okay. Without clearing your register, without doing more than one, without adding any rounding error, divide that by 1.33. And then take the inverse sine of it. (7.5 degrees). So if this was 10 degrees, this is only 7.5 degrees. All right. That's actually, what, 3/4, which is what they got with their small angle approximations, but I don't want to go through having to explain why that works. Okay, that means we now know that sine of 7.5 degrees is equal to what? One meter. Right? But what would this angle actually be? Right here. Enclosed angles, enclosed opposite angles. If this is 10 degrees here, then this is also 10 degrees here. Which means our apparent depth is going to be the sine, well, it's going to be, what would the sine of 10 degrees be? Yeah. 0.17. So I'm not sure. We would have to actually know this length or this length. Well, we can calculate this length because this is the cosine. No. This is, oh, yes. I'm sorry, people. I've been trying to do this upside down and I've reversed my functions. What is this depth here? 1 meter. If this is the angle, theta 2, this depth is not the sine of that angle, it's the cosine of that angle, is 1 meter. So we find that 1 meter is equal to this length times the cosine of 7.5 degrees. And that the sine of that length times the sine of, which time are we running out of? Fast. Yeah, this is I can see why they did the small angle approximation, because we're going to have to end up converting it into a tangent and actually doing the arithmetic. And I don't want to try and do that impromptu. So they did end up coming with the actual depth divided by the index of refraction of the medium, which would be 3/4 of a meter. But yeah, I don't want to turn this into a trig class. Let's stick to learning the physics. So let's move on, because we do need to cover these thin lenses. And we're going to find that it's actually very much the same as the concave and convex mirrors. We're going to end up with pretty much the same equations. That being the case, let me ask you to think about something. Why do they call them thin lenses? That's the next section. Section 23.7, thin lenses, ray tracing. Why would they call them thin lenses as opposed to what? As opposed to thick lenses. So what would be the difference between a thin lens and a thick lens? It is, but why? Why are thick lenses thicker than thin lenses? No. Let me give you, how many of you have ever heard of, say again? Yeah, but the question is, that's definitely a consequence of it. How many of you have heard the word Fresnel, as in a Fresnel lens? Do any of you know how to spell Fresnel, as in Fresnel lens? Fresnel. And there goes that cap, right under Caleb. Thank you. We're going to do ray tracing, and we're going to look at this. We're going to look at a lens. It is, well, I'm going to make it more exaggerated than that, which will actually play right into the question that I raised. That's a lens. So light hits it here. It comes straight through at 90 degrees because the angle of refraction, n times sine 90, n1 times sine 90 equals n2 times sine 90. Comes right straight out the other side. Is that true? Yeah, this isn't 90, this is 0. That's right, thank you. That's 0 degrees. So 0 times 0 is 0. Thank you. You move up a little bit, and your light ray comes in here. Now the angle is not 0 anymore. And so you've got this, because this, assuming this is greater index of refraction, this is going to bend towards the normal, come out here, and go straight. Same angle that it leaves with. Okay, now if the other side of this lens were curved, well then it would bend again and it would come to a focal point. But right here, the further away you get, the more the light gets bent towards the center. Okay? Does it really matter how far it passes through here? What Fresnel did was he said, well, let's take this little chunk of the lens and cut it out. And then we'll take this little chunk of the lens and cut it out. And then we'll take this little chunk of the lens and cut it out. And that's a Fresnel lens, where you have basically the curvature of that whole arc in little segments. All the way down to some center point. How many of you remember those old overhead projectors? You've seen this kind of a lens before. It's just a flat piece of plastic, but it's got concentric rings that still magnifies. See it in taillight lenses? It used to be very common in traffic lights and tail lights and headlights even. That's called a Fresnel lens. And that's all it does. That's all he did, was he took all this extra mass of glass and got rid of it. And still got the same amount of, the same mechanism of bending the light through and out the other side. Well, I drew it on this one as a flat on the one side. In fact, lenses can be convex or concave, or in fact, they give a list of the type of, there's 6 different types. And while I'm thinking about it, has everyone signed this? You haven't. There you go. They list 6 different types. They're in 2 classes. There are converging lenses, and there are diverging lenses. All right. They can, now every lens surface can either be convex, planar, or concave. Now, if a lens is double convex, it is a converging lens. If it is plano-convex, and that's plano as in planar, as in flat surface. It has nothing to do with the town in Texas. And then it can be convex meniscus, where one side is convex and the other side is concave. How many of you have heard the word meniscus before? Can you tell us what a meniscus is? Have you ever learned how to measure liquids in a beaker? It has to do with the deformation of a surface at an interface. Okay, so if you put water in a glass, the meniscus forms concave. The water tends to climb up the sides of the glass. If you put mercury in a glass, it forms a convex meniscus. That the mercury is kind of repelled away from the glass wall. Okay? Convex meniscus means it's convex on one side and concave on the other. Now, you can also have double concave. Can anyone guess what that one is? Planar concave. And then concave meniscus. Now, I want you to think about this. What is the difference between concave meniscus and convex meniscus? You're right, exactly right. It's which side does the light come in on? That is, but he's right. That is the whole difference between convex meniscus and concave meniscus is which side faces forward. In general, convex curves will produce convergent rays coming out the other side. Concave will produce divergent rays coming out the other side. And that had something to do with over here that we started. What was I talking about before we... don't make me rewind the tape. That was a diversion from something I was saying over here. No, each piece actually has a curvature to the little segment that would perfectly match the curvature of this big lens. But it's only the outside surface that he kept. Okay? And understand, a Fresnel lens could be plano-convex, like I've shown there, or planar concave. So that instead of looking at that enlarged, instead of being this shape, it could be this shape. All right? And I may have drawn that backwards, but you get the idea. In fact, I would have drawn it. If it were concave Fresnel, it would be like this. Okay? A planar concave. But a Fresnel lens can be any one of these six. It can be double convex, planar convex, convex. It's the geometries of the two sides. It's like you take this lens, you cut out a slice, you preserve this piece of geometry and this piece of geometry, and you get rid of all the middle. Okay? And we will pick up ray tracing and looking at the equations of lenses. Don't pack up so fast. I didn't say go anywhere yet. Giving you a heads up. This is where we're going next time on Friday. We're going to look at lenses. We're going to develop the lens. We're going to look at the equations of how to analyze lenses. What's a diopter? You go to the Walmart to buy a pair of these, because I keep reading glasses scattered all over the place. I literally have dozens of them, because I can buy dozens of these for a fraction of what it would cost me to go get a pair of prescription glasses. Okay? But when I go buy them, I have to say, well, what power, what diopter do I want? We're going to find out what a diopter is. We're going to find out the equations that cover these, that we use to analyze lenses, and we're going to discover that they're very much the same equations that we use for mirrors. Okay? But we still haven't answered my question. Given that we know that the equations are going to turn out to be the same as the equations that govern mirrors, why call them thin lenses as opposed to thick lenses? They are a lot thinner, but why? No, think about spherical aberration. What caused spherical aberration in our spherical shaped mirrors? The sphericalness of the mirror, exactly, because the light coming in at all diameters of that sphere do not all converge to a single focal point. In order to accomplish that, you would have to grind a parabolic mirror. How did we get it close enough that it didn't matter? You'll really need to remember this. How do we combat spherical aberration in mirrors? By keeping the diameter of the mirror much, much smaller than its radius of curvature. The same thing applies to lenses. When the diameter of the lens is much smaller than the radius of curvature of the lens, it's considered a thin lens. Okay? And it has to do with Fresnel. Suppose we've got this spherical lens, and we're going to make a double convex. So we got this big lens that's just a spherical ball. That's the midline. Well, we're not going to get anything close to a good single focal plane over here. But if we restrict the lens to just this little slice, this little core right out of the middle of the big spherical crystal ball, then this diameter of the lens is much smaller than the big diameter of the radius of curvature. Okay? If this D is much, much less than R, then this is considered a thin lens, because look what happened if you follow in Fresnel's. You take this piece over here and this piece over here, and you cut off just those curved ends and put them together. Now you end up with a thin lens. If this D much, much less than R were not true, then you end up with a lens that looks more like this. Only a lot nicer. And it's not even close to thin anymore. So that's the last take home for today. The fact that it's a thin lens means that the radius of curvature of the lens surface is much greater than the diameter of the lens itself. See y'all on Friday.